Today I'm presenting Lab 3, Magnetic Field of a... In this lab, we had systems and surroundings. So the system was the bar magnet and the phone that we used. And this phone acted as the observation location. Everything else was the surroundings. And so the bar magnet and the phone were oriented differently. That was the gist of the lab. But the fundamental physics principles listed here, we'll get to more detail later. But it's essentially the formula of a magnetic field. And here we're noting specifically that at a far distance, the magnetic field's perpendicular is half the size of the magnetic field's parallel. The main result is that the magnetic field increases in magnitude as you get closer to a magnet, therefore as R decreases, and the initial conditions are the predetermined bar magnet and its strength, and also the predetermined values of the magnetic field, 20, 70, 120, and so on, the increments that we measured at. And then also the magnetic field in the x direction is 0, and we do this to make sure that all the magnetic fields gained in the x direction is due to the bar magnet. So here is the formula for a bar magnet, and this applies anywhere it is. Mu naught is 4 pi times 10 to the negative 7, and mu is the magnetic momentum, and then R represents the distance or the R vector. And then the magnetic field of a bar magnet is shown here, and notice how it is pointing in the North Pole direction and how it kind of loops back to the South Pole. Okay, so the first thing we did in this lab is we oriented, we made our initial conditions. So that X there is the reference point determined by leveling out the phone and deciding where it was the best. So for example, the first thing to do to initialize this was to make X as close to 0 as possible. This was to make sure that all the magnetic field due to the Earth was like as low as possible in the x direction, so that we lined up the phone and the measurement exactly with the magnetic field of the Earth, and therefore all of the magnetic field of the Earth was in the y direction. And so that perpendicular orientation really helped in this experiment. And we also moved the phone around to find our reference point in our calculations. So then the lab procedure was that we moved the phone closer and farther away from this bar magnet like that, and we also moved the phone at a perpendicular angle, and you can see that's a 45-degree angle there. And we did this at set magnetic fields, and then we calculated or got our R values, and so we were able to see the relationship between R and the magnetic field. So our observation is that when the magnetometer is far away from the magnet, it measures a near zero magnetic vector in the x direction. As the magnetometer moves closer to the magnet, then it measured the x component of the magnetic fields increases, and then Earth's inherent magnetic fields is taken into account, and therefore x begins as 0, and the sign of magnitude of y represents Earth's magnetic field, and also that bx was positive, and that therefore it means the North Pole is closer to the polar. So assumptions and errors. We assume that there is no magnetic field caused by the electronics around while the lab was conducted, or Earth's magnetic field in the x direction. It assumes the app we used is accurate and that the point of reference is measured accurately. This is the code we used, and it is based on this formula for the magnetic fields manipulated. And this is the data we collected. This is what the model looks like. So notice how the orange arrows are parallel, and they are twice the size of the blue arrows, except for this one blue arrow in the middle, and that only looks like that because it is closer to the to where we're observing it from, because it's on a different axis. Then the purple arrow in the corner, it's at a farther distance, and that's why it's smaller, but that is at a 45-degree angle, and notice how it's oriented the same way the magnetic field looks in this picture for a bar magnet. Okay, so similarities and differences. Similarities between our data and our computation model is that there's a 1-to-2 ratio for that split between the perpendicular and parallel magnetic fields, and the measurements are relatively close to the average measurements in the computation model are relatively close to the average values in the collected data. And the difference is that the data presents more variability, and it's a less direct pattern as the data is collected rather than mathematically calculated. So what if we hadn't oriented the experiment to compensate for the magnetic north and instead laid out the meter stick at some intermediate angle with respect to Earth's magnetic field? The Bx wouldn't solely be caused by the bar magnet, and the magnetic field in the x direction caused by Earth's magnetic field would have to be accounted for and subtracted from the observed values to obtain the bar magnet's magnetic field. And if we were to stick two identical magnets together end to end, the measurements would have a greater magnitude but be a similar orientation.